So I have the applications assignment up here, and for this video I'm going to work on question 1. Now we have a word problem here. There's no picture, so this might be hard to conceptualize. So let's sketch out a picture. We can sketch out a picture with either scratch paper or using Autocad. I'm going to use the Autocad because we probably all could use a little review, a little practice with Autocad. So I know my three numbers. It says the sides of a pattern. So we have a pattern that we're working with, and we have sides. So that means the numeric information that comes after this is it's going to relate to the sides. It says it's in the shape of a right triangle. Okay, so we know we're dealing with a right triangle. It's going to be a trigonometry problem. They measure 10.6, 23.5, and 25.78. Now how I'm going to decipher which side is which is by their sizes. I see that 10.6 is my smallest side, so that's going to be the smallest side of the triangle. See that 23.5 is in the middle, and 25.78 is the largest, which this means that this is going to be the hypotenuse. The hypotenuse is always the largest side. So from this I can sketch a picture out. The question is, what is the measure of the smallest angle of the pattern? So here's my purpose statement. Here's what I'm looking for. I want to look for the smallest angle. So first let's sketch the triangle out to conceptualize it, find the smallest angle, and then apply what we know about trigonometry to move forward. So I have AutoCAD here. I know it looks a little weird. We haven't been in a while. I'm going to draw a triangle using the polyline function, and I'll use grid snap to snap to the center point. But this doesn't matter a whole lot, right? If I use grid snap or not. But what is important is that for the two sides that are not the hypotenuse, I have orthographic projection on or grid snap, whichever will allow me to input values in the horizontal or vertical direction. For my 10.6, I'll do that horizontally. And then my 23.5, I'll do vertically. And I did not mean to get out of the polyline command, so I'll redo that really quick. So polyline, I'll start at the origin. I'll do 10.6, 23.5. And I can close my rectangle. I actually don't even need the hypotenuse to draw this triangle. I can hit close in AutoCAD, the C key on your keyboard, to finish it off. And now I'm going outside my grid, so I'll turn the grid off for clarity, add some dimensions on this boy, or on this triangle. Oops, looks like I need an align dimension for this one. So I'll go to the aligned option for the dimensions. I know this is bringing back memories. I got object snap on, allowing me to snap to the corners. And I can't see those values very well, right? So I'll select them, go to properties, and I'm going to change the annotative scale, which is in fit. The dim scale overall, I can change it to like 8, and it scales everything up by 8, which is nice. I'll bring these out now. I got my values. You all see that 25.78. So at this point, I'm going to get out of the AutoCAD environment because I do want to use trigonometry principles to solve this, even though I could probably solve it with AutoCAD. I'm going to go to my notebook and snip a picture of this triangle really quick. And now, where is my smallest angle, and how do I know which angle is smallest without actually knowing angle information? So I can visually see that this angle right here is bigger than this angle. We know the angle is biggest the wider it opens up. So here's our small angle. let's denote this as angle A and this as angle B. And now we can use trig functions to solve for the smallest angle being angle A. I would preferably want to use the easiest trig function ratio to solve for this triangle, or to solve for the angle. But bar none, I know I'm going to need an inverse trig function. But first let's write all the trig functions down, see which ratio is going to be easiest to work with. So SOHCAHTOA, I have sine of A equals the opposite over the hypotenuse. This is going to be 10.6 over 23.5. I have cosine of A, so it's going to be adjacent. And whoops, I actually realized a mistake that I made. This should be 25.78. Sorry about that. And then for cosine, we have 23.5 over 25.78. And then for tangent of A, we have 10.6 over 23.5. Now, which numbers to you seem like the most even, the most round numbers, the easiest numbers to work with? It's going to be the 10.6 and the 23.5. Those only go up to 3 significant digits. The 25.78, that's probably a really long decimal. If we were to use these nice round numbers to calculate out the hypotenuse, it would actually be a pretty long decimal. So let's use these nice round numbers first. Okay, so tangent, we're going to use tangent. We can gauge from our, let me erase this all really quick, and then I'll scroll up a little bit. We know that we can solve for the angle given a ratio. We don't know what the angle is. The angle is a mystery. But we know the ratio. We know the ratio. So, from Module 1, we saw that given a ratio, we can solve for the angle using the inverse function of whatever trig function we have. So here we're going to have inverse tangent. I can solve for this using algebra by taking the inverse tangent of both sides. So the inverse tangent of A is equal to the inverse tangent of our ratio. We're just solving an equation now, right? These tangents are going to cancel out on this side, and we'll only be left with A equals the inverse tangent of 10.6 over 23.5. Here's where we can get our calculator. So I have my calculator right here. I'm going to do 10.6 divided by 23.5. That equals, whoops, I noticed an error in my calculation. Do you see that? So I'll redo that. 10.6 divided by 23.5. We get 0.45106383. If I take the inverse tangent of that, so I'll go to the second key or press tan twice to get the inverse tangent of my previous answer. I get 24.27841369, or 13673. Now in our original question, with our given numbers, we had certain amounts of sig figs, right? If we remember, our final answer can only be as accurate as the least accurate number in our given information, and accuracy is gauged by significant digits. So our number with the least significant digits, it's the 10.6 and the 23.5. That's 3 significant digits. I have 1, 2, 3 significant digits on the 10.6, 3 significant digits on the 23.5, 4 significant digits on the 25.78. 3 is less than 4, so 3 sig figs is what I got around to. If I look at my final answer again, 1, 2, 3 sig figs, that's going to round to 24.3. So I'll go and write that over here. My final answer is 24.3. Would you like to know a good way to check your answer? Oh, and this is in degrees, sorry. You can take the tangent of 24.3 and see if you get your ratio back. Another way, using Autocad, that we can check our answer is to put a dimension on this angle. So I'll go this side, that side. It shows up as 24, but remember, this might not be showing the whole precision. So I'll go to properties, and now I'll change the precision in properties. That's under primary units. Under angle precision, I'm going to go to 3 decimal places. Or, sorry, not 3 decimal places, but 3 significant figures. I got 24.3. That's the answer that I calculated. Yay! So there we go.